Let's start by doing some examples of graphical problems with the second derivative. So I'm looking in section 2.5 right now. I'm going to use a hard copy of the textbook. And you can see in problems 19 through 24 that we've got some graphs. And the directions say graph the second derivative of the function. Let's go ahead and do number 21 right here. So there's our function, f of x. The goal is to draw a reasonable graph of the second derivative. I think it probably is best to start by graphing the first derivative. So there's f of x right there. Let's draw a reasonable graph of f prime of x. How? We've done this before. Take a look at this graph and ask what the slopes are. When x is -4, the slope of the tangent line is pretty big. If you imagine drawing a line right there, tangent to the curve, it probably would go up here. Y would probably increase by about 5 or 6 units as x increases by about 1 unit. That means the derivative when x is -4 is up here around 5 or 6 in value. Let's say 4 is right here. I'm just going to draw a point right there. This doesn't have to be perfect. You're just after pretty good. As x increases from -4 up to right around there, that looks like that's -1.7 or so. Here's the origin, by the way. Here's -1, here's -2, -1.7 or so. That's where this graph has a horizontal tangent line. The tangent line at that point, right about there, is horizontal. If you zoom in closer and closer, it's going to look more and more like a horizontal line. So if I mark -2 right here, just to the right of that, where an x is about -1.7 or so, that's where the derivative is going to be 0. The slope of the tangent is 0. It's positive before that point, but notice it's concave down right here. What does that mean? It means the slope decreases. Concave down, yes, this looks like part of a frown or an entire frown if I go up here. But more importantly, the slope is getting smaller. It starts out close to 5 or 6. When you're right about here, the slope might be 2 or 3. And then when you get to this point, it goes down to 0. So something about like this is how the graph of the derivative starts. By the way, this graph does look like, you might say, a cubic, a typical kind of cubic graph. It is also true that the derivative of a cubic is a quadratic. If it indeed is a cubic, then what we're drawing really is a parabola. But there's no guarantee that it's a cubic for sure. You can't really completely eyeball it. It might just look approximately like a cubic. As x continues towards 0, the slope continues to decrease, now through negative values, and is a largest negative slope furthest away from 0, right about there, close to where x is 0, maybe slightly negative, -0.1 or -0.2. If you imagine this to be a hill and you're skiing down the hill into this valley here, that's where you're going downhill the most steeply. Right around here, say, is where this graph has a minimum. X is ever so slightly negative. Then, as you continue increasing, now the slope is getting bigger. It's still negative over here, but it's now getting flatter. The slope itself is going towards 0. And when x is about positive 1.5 or 1.6 or so, that's where that slope is 0 again. So if 2 is right here, I'm back up towards 0, right around there. And then after that point, the slope is positive and continues to increase. The graph has become concave up again, or concave up for the first time, I should say. So there's an approximate graph of the first derivative. The second derivative is the derivative of the derivative. So now to draw the second derivative, as a function of x, I want to think about slopes of this thing. When x is close to -4, the slope is definitely negative, but coming closer to 0 and equaling 0 when x is slightly negative, right there is where the slope is 0. So the graph of the derivative of this one needs to start out negative and head towards 0 and be 0 at approximately that point. Now, I started to draw it curved. And again, in theory, we don't know for sure this is a parabola, and so it might be slightly curved. But if indeed this is a parabola, if this is the graph of a quadratic, its derivative will actually be linear. Even though I drew it curved, it really should be straight if this indeed is a quadratic. I made it be 0 when x is slightly negative, corresponding to this value of x. Then it becomes positive and continues to increase because now this graph has a positive slope that keeps getting bigger and bigger. This one's concave up, looks like a smile. Yes, concave down, looks like a frown. Hey, it rhymes. Or part of a frown. In reality, it means the slope is decreasing, either through positive values towards 0 or through negative values further away from 0, or both combined. Concave up looks like part of a smile or an entire smile. Technically, that means the slope is increasing, either through negative slopes towards 0 or through positive slopes that keep getting bigger and bigger, or both. The second derivative tells you where the original graph is concave down and where it's concave up. Take a look at this red graph and compare it with the original graph. This red graph is negative when x is less than this number, about -0.2. That's where this graph is concave down, part of a frown or a full frown. Right there, that's where that graph's concave down. When f double prime becomes positive, that's where this graph is concave up, a smile or part of a smile. The place where the graph changes concavity, right about there, let's call it an inflection point, where the graph changes concavity, where the second derivative changes sign, either from negative to positive, like it does here, or it could be the other way around, from positive to negative. It's called an inflection point. Where the first derivative is 0, changing sign in particular with this graph, you have what are called local maxima and local minima, high points and low points. The top of a hill right there, the bottom of a valley right there. Those spots, when x is about -1.7 and when x is about +1.5, are spots where the first derivative changes signs. Here from positive to negative, and then right there from negative to positive. Giving you a lot of verbal and visual information here to process that you might be feeling seems somewhat reasonable as you're sitting here. But then when it comes to exam time, if you don't think about this again, you'll probably forget it. So that's the key in math, as in many things. You got to do things consistently to get it to stick in your head. Can I clarify anything? Good question. Was that related to your question or not? No? Okay. Good question. Will derivatives of an arbitrary function eventually get to the point where they're straight? The answer is actually no. There are plenty of functions, cosine of x, for example, being one of them, whose first derivative, second derivative, third derivative, fourth derivative, fifth derivative, etc., never get more straight. In fact, they always look like a sinusoidal wave. But that's a good question. It does happen with polynomials. And in fact, the third derivative here, yes, there is a third derivative, f triple prime of x, is the derivative of the second derivative, f double prime prime of x. It is the slope of this one. And if this one's straight, then this one's going to be constant. Whatever constant slope this is, that's what the value of this one is. And since that one's constant, the fourth derivative, f quadruple prime of x, which is the derivative of the third derivative, if this one's constant, having 0 slope everywhere, then the fourth derivative is also constant. having zero slope everywhere, but moreover, it is always equal to zero. It's the x-axis. In physics, if your original function is the height, or a position even left and right, then its derivative is the velocity. We've seen that. Its second derivative is the acceleration. Its third derivative is called the jerk. I'm serious. The jerk. Jerk your head, right? Hit that accelerator on your car too hard, you're going to have a high jerk and might snap your neck. Hopefully not. Yeah, it gets even funnier. The fourth, fifth, and sixth derivatives are called snap, crackle, and pop. Rice Krispies. Yes, I'm serious. That's what they're called. You don't want a high pop. Probably for sure you'll need surgery. Yes, we could keep going. You can keep taking derivatives forever. At least if your function is nice enough, which almost all of our functions are. The strange examples are the piecewise examples. Another question? Derivatives? Primes? Yeah, there is a notation for an arbitrary number of primes. If you write f with an n inside parentheses of x, this is notation for the nth derivative. So if n is 1, that's the first derivative. If n is 2, it's the second derivative. If n is 3, it's the third derivative. Instead of writing an arbitrary number of primes, this is just shorthand notation. It does not mean nth power. It does not mean the same thing. The corresponding Leibniz notation for this is this. And yeah, this is a little confusing. I said this on Wednesday. I'll say it again today. Notation is important, okay? If we've got a function y equals f of x, dy dx is the Leibniz notation for the derivative of y with respect to x. That is f prime of x. You could think of this as d dx of y. Technically speaking, these are slightly different notations for the same thing. They do mean the same thing in the end, but it's sort of a way of thinking about things. When you write it as a plain old Leibniz dy dx, that's the situation where you're pretending dy and dx are individual quantities and this is a fraction. It's not literally a fraction. It's just helpful to pretend that sometimes. If you see that kind of thing in your science textbook, your science textbook might treat it like it's a fraction. They're really just pretending. They're not doing rigorous math. I always, in my physics class, I'd be there, and yeah, Beacon was one of them, the professors. I'd be like, well, how do you know you can do that? How do you know you can pretend it's a fraction? And they'd say, well, what are you, a mathematician? Okay, you just do it. Because once you've worked with this stuff enough, it just makes sense. I'm serious, it just makes sense to them. I will talk about, especially with integrals, why it makes sense later on in the course. But they're not doing rigorous math. Don't think they're doing rigorous math when they do that. They're doing hand-wavy, magical math. Convenient fictions. Calculus is full of convenient fictions. It's always very confusing because of that. Just realize that it's not rigorous math. It's okay. If you're more mathematical bent, you like seeing proofs, just realize they're not doing proofs. They're developing intuition. When you write it this way, you think of this d dx as being what's called an operator, telling you to take the derivative with respect to x of whatever function of x that you have there. Now, you don't see an x there, but it's assumed y is a function of x. When you talk about the second derivative, f double prime of x, here's the function notation for it. But you also can think of it as the derivative with respect to x of the first derivative, dy dx. And then it's as if you pretend you're multiplying. D times d is, d squared. And I guess the y is just by itself. And then dx times dx is, I guess, dx squared. And there's the Leibniz notation for the second derivative. But you're not actually multiplying. You're just pretending to. for the sake of fun, convenient notation. I'm serious. Yeah, it is partially meant to be fun. Okay. In reality, you're not multiplying here. There's not a multiplication going on. There's a composition of operators, if you will. You could also put the ddx in front of this. ddx is an operator, and operators are actually functions themselves. ddx is taking an input, a function, y, a function of x, and giving you an output, a derivative. That's what functions do. Give me an input, I'll give you the output. But it's not an ordinary kind of function that you can graph. It's just a function you think about. I don't graph ddx. I just think about it. It just means take the derivative of whatever's inside the parentheses. It's an operation, a function. What's its domain? That's not so clear. I'm not going to get into that. And you can keep going. ddx of the second derivative is the third derivative, and you could write that like this, as if you're multiplying d and d squared to get d cubed, and as if you're multiplying dx and dx squared to get dx cubed, but you're not really multiplying. It's just a fun pretend way to think about it. It's convenient that the notation works that way. It's kind of fun, kind of nice. But yes, it does sometimes end up being confusing. See, what the reason you got all these weird, confusing things going on is partially historical. Okay, Leibniz did think of dy dx as an actual fraction, dy and dx as individual quantities. He imagined them to be what are called infinitesimal quantities, positive numbers that are smaller than any number that you know of. But wait a minute. There don't exist such numbers, right? Because you take a small positive number, you can always make a smaller one, but dividing by 2, right? So how can there be positive numbers that are smaller than any number you can think of? It's a pretend kind of thing. It was a useful fiction. In the standard real number system, it's a pretend kind of thing. There's actually something called non-standard real numbers, hyper real numbers, where it is rigorous. Oh, most people say mathematicians must be crazy to think of these things. Mathematicians say, fun. It's fun to think of these things. Doesn't mean it's easy, but it's kind of fun. Okay, let's do some practical word problems as well. Now, when I say practical, I don't mean that I'm actually solving some real life problem to help me buy stocks, for example. It means I'm thinking about how to think of these real life situations mathematically. That is a prerequisite to being able to do advanced applications. You can't do advanced applications of math unless you learn how to think mathematically about them. And in particular, you can't do advanced applications of calculus unless you learn how to think about them with calculus ideas and notation. 25 says, let P of T be the price of a share of stock of a corporation at time T. Oh, lots of funny stories today. Well, it's on my phone. So when crypto was going on, a really big thing a few years ago, I'm like, I don't want to get into crypto. Then my kids convinced me, Dad, you got to buy crypto. So I did. I bought Bitcoin and I bought Ethereum in April of 2022. And if you follow cryptocurrencies, April of 2022, it nosedived. Okay, right after I bought it. In fact, I lost $10 in the first minute. I bought $1,000 worth. I lost $10 in the first minute. And it went down to like as low as 400. I lost 60% of my value. It's back up a little bit now, but who knows what it's going to do. Anyway, so this is stocks. Stocks go up and down as well. Not quite as fast as crypto. What does each of the following statements tell us about the signs positive or negative, of the first and second derivatives of P of T? A, the price of a stock is rising faster and faster. B, the price of a stock is close to bottoming out. Focus on A first. Now, okay. In reality, stock prices do this kind of thing. Okay, that's what stock prices look like in reality. They're going up and down pretty much every minute of every day. But for the sake of doing the problem, we're pretending they don't. What does it mean for the price of a stock to rise faster and faster? Well, first of all, it's rising, going up faster and faster, rising faster and faster, getting steeper and steeper in the positive direction. For A, 25A, we're assuming the price of the stock as a function of time looks like that, increasing in concave up. So as far as the sign, it means P prime of T is positive because it's increasing. And P double prime of T is positive because it's concave up. In B, the price of a stock is close to bottoming out. It's doing bad, but it's not getting as bad, maybe. Bottoming out, it can't go below zero. It's decreasing, but concave up. It's close to bottoming out. It can only bottom out at zero. So the first derivative is negative because the slope is negative, the graph is decreasing. The second derivative, however, is positive. The graph is concave up. Here the slopes are positive and keep getting bigger and bigger. Here the slopes are negative, keep getting closer to zero, which means they're getting bigger and bigger. As negative numbers go towards zero, go up towards zero to the right on a number line, that means they're increasing, they're getting bigger, so to speak, where bigger means further to the right on a number line. Sometimes I'll use the phrase big negative number, and when I do, then I mean really further to the left on the number line, because I'm saying it's negative already, and by big, I mean far from zero. So that's a little hand wavy. But sometimes we say that kind of thing. You just got to realize it. 26, concentration of nitrous oxide. Isn't that laughing gas? I think nitrous oxide is laughing gas. Oh, another funny story. So the first time I had a cavity, I've had hardly any cavities in my life, like 2 or 3, whereas opposed to my wife's had like 15. First time I had a cavity, though, I had it filled. The dentist gave me laughing gas. I was like, I don't know, 8 years old or something. I had no idea what I was getting into. I hallucinated while he was working on me. I was aware of things. He was talking to me, but I hallucinated that my eyes were inside my mouth and I could see him working. And I didn't think anything of it. I'm like, cool, what's he doing there? And then we took the nitrous oxide off, the laughing gas, and then everything was back to normal. It's in the air, it's increasing faster with time. Look for keywords, increasing faster. That's like in 25, the first situation. Right there, increasing faster and faster. So both the derivative and the second derivative are positive. Should be able to do things like B. If a graph is increasing in concave up, which of those is larger? The second one, because the graph gets higher as the input increases. And which of those is larger? The second one as well, because the graph's getting more steep in the positive direction. On the other hand, for a decreasing in concave up graph, the function values are bigger when the input is lower. But the slope is bigger when the input is higher. Bigger being meaning closer to zero in this case with negative slopes. 28, a headline in the New York Times reads, a steep slide in law school enrollment accelerates. A steep slide in law school enrollments accelerates. What function is the author talking about? I guess law school enrollment is a function of time. Each year, a certain number of people enroll in law school. You keep track at the beginning of each year, maybe each semester, September and say January. How many people enroll? It keeps going down. It is a slide. The graph's going down, it's decreasing. But it says a steep slide accelerates. That has an implied meaning of getting faster and faster. This one's got to be decreasing and concave down. If it's accelerating, it's decline. Now, it can't keep doing this, right? Because otherwise the enrollment's going to go negative, which I suppose could happen when more people drop out than are signing up. But for the purposes of only thinking about people enrolling, it can't keep going like that forever because it can't go negative. But at the moment, what the headline is saying is that the graph is decreasing because it's a slide. That slide is accelerating. It's getting steeper. It was steep to begin with, but it's getting steeper. It's accelerating. Both the derivative and the second derivative are negative. And industry is being charged by the EPA, Environmental Protection Agency, with dumping unacceptable levels of toxic pollutants into a lake. Over a period of several months, an engineering firm makes daily measurements of the rate at which pollutants are being discharged. They're taking daily measurement of a rate at which pollutants are being discharged into the lake. How fast? They're not actually measuring how much pollution is in the lake. I guess they're sitting there by the discharge sewer or something and measuring how fast the pollutants are coming out. That's easier to measure than the total amount of pollutants in the lake. The engineers produced graphs similar to one of these two figures. I guess they're saying both of these are possibilities. For each case, give an idea of what argument the EPA might make in court against the industry and in the industry's defense. So these are just two different scenarios. Take them one at a time. Here, we got a graph versus time of the rate of discharge that is increasing. That is technically a bad thing when this graph is increasing. It means the pollutants are coming out faster and faster over time. So as far as against the industry, you would say that. You'd say the pollutants are coming out faster and faster over time. In favor of the industry, it's a concave down graph. Yes, they are coming out faster and faster, but the rate at which that rate is changing is negative. The second derivative is negative. The rate at which the rate is changing is negative. They're coming out faster and faster, but less fast than they were at the beginning. Would be another way to say that. The graph is less steep over here than it is over here. Okay, if I just say these things verbally and tracking with me. Here, the rate of discharge is going down, so over time, there's less and less pollutants coming out. Against them, it's still positive, however. So the EPA would say, hey, they're still polluting. But in their defense, the rate of discharge is going down. It's less and less pollution over time. 40 is a physics problem. This graph gives the position f of t of a particle at time t. This is position. It's not velocity. It's not acceleration. We want to figure out where the position and velocity are positive and acceleration. Where's the position and velocity decreasing? It's pretty tricky here. Is this up-down motion, left-right motion, something else? They don't say. It could be up-down motion. It could be left-right motion. The vertical axis here doesn't have to correspond to a height, for example, though it could. Although if it's negative, it means you're underground. It's a position. The starting position is negative. That's not a typical thing to do in most applications. In most basic physics applications, you would take the starting position to be 0. Choose your number line in such a way that your starting position is 0. They didn't do that here. They chose the number line. They chose the origin to be in a spot where the initial position is negative. Let's go ahead and let's imagine this with left-right motion, actually. Not saying it is left-right motion, but let's just imagine it is. I'll go ahead and label that with the letter X, representing an X-axis, and I'll go ahead and make an arrow pointing to the right, indicating rightward motion is positive motion. Rightward direction is the positive direction. If I decide I want the origin to be there, if that's 0, why? Just because I feel like it. Maybe that's where my ham sandwich is that I'm moving back and forth to try to grab, but I keep missing it or something. My initial position is negative. As time starts to increase, it becomes more negative. That means I'm moving to the left. A little ways. When you get to this moment in time, that's where this graph has a horizontal tangent. That's where you turn around, because now the position starts increasing. So you start by moving to the left, then you move to the right. Once you get past this point, you're into the positive values of X. Continue moving to the right until you reach some maximum value of X before you turn around and come back. Towards 0, I guess I reach my sandwich in the end. Now I drew this as kind of like an S shape, backwards S shape. Realize that in reality, you're just going back and forth. That's just for visual clarity. You're moving to the left, turn around, move to the right, turn around, move to the left. End at position 0 because this graph is back to the horizontal axis at that moment in time. So as far as where the position is positive, it's when you're to the right of that horizontal intercept at T3, T4, and T5, at those values of T where the position is positive. Position is negative at T1 and T2. Where is the velocity positive? The velocity is the derivative of position, the slope of the position graph. Positive at T2, positive at T3, and those are the only 2 spots of the mark spots. At those moments in time, you are moving to the right. That's a positive velocity. When you move to the left, it's a negative velocity. Where is the acceleration positive? The acceleration is the second derivative of position. It's going to be positive where this graph is concave up. T1 and T2. And maybe also T5. It's a little hard to tell, but I think it's slightly positive, concave up there. How is that related to the motion? This is the trickiest part. We're used to thinking of acceleration like when we're driving our car and we hit the accelerator, we're speeding up. That's a positive acceleration. In this left-right motion, it's only a positive acceleration when you speed up as you're moving to the right. If you're moving in the negative direction, it's actually a positive acceleration when you're slowing down, because the acceleration is positive if you're slowing down as you move to the left in the negative direction. If the velocity is negative, but you're slowing down, that's a positive acceleration. The velocity is getting bigger, technically. Where is that happening? It's happening at first. We started off with a fairly high velocity, 8 times 0, in the negative direction. Then we got to slow down if we're going to turn around. Once we turn around, we continue to the right, speeding up as we go. Speeding up until the graph becomes concave down, right at the inflection point, right about there, which is not a marked value of T. Graph is concave up here until about there. Then the graph's concave down. That means your acceleration is negative, sometimes called a deceleration. Negative acceleration is when you're slowing down as you move to the right, as we're doing as we reach this turnaround point, or when you're speeding up as you move to the left. That's a negative acceleration. The position decreases where the velocity is negative. That's at T1, T4, and T5. That's when you're moving to the left when position is decreasing. The velocity is decreasing when the acceleration is negative. When the second derivative is negative, that's occurring at T3 and T4, because that's where the graph is concave down. Once again, it's something where you might be sitting here and saying, yeah, I get it, but then you get home and you don't get it. Okay, you got to rethink about things carefully. Can I clarify anything there? I pretended it was left, right. It could have been up and down. Another question? Go ahead. The answer to C, where is the acceleration positive? It's where the second derivative is positive. That's where it's concave up T1 and T2. Did you catch my train of thought there? Acceleration is positive, but where the second derivative is positive, where the original graph is concave up. T1, T2 also, excuse me, also T5. It's ever so slightly concave up there.